Okay, so in this video we're going to solve systems of equations in two variables. So a system of equations is composed of two or more equations considered simultaneously. For example, x plus y equal to 1 and the equation 3x plus y equals 7 is a system of two linear equations in two variables. The solution set of such a system is the set of ordered pairs that make both equations true. And so let's see what we mean by this. So determine whether negative 3, 1 is a solution of each system of equations. So we'll start with A here. And all we're doing is just substituting the ordered pair into the corresponding equation. So we'll test the first equation here. 2x plus 5y equals negative 1. So we plug in our negative 3 into for x and our 1 for y. And does this equal negative 1? Well, we would get negative 6 plus 5, and negative 6 plus 5 does equal negative 1. So that is indeed true. So it satisfies the first equation. What about the second equation? Well, let's see. Plugging in our, once again, we have x minus y equal to negative 4. So we would have a negative 3 minus 1 equals negative 4. Is that true? Well, this is negative 3 minus 1, so that's negative 4. And that indeed does equal negative 4, so that checks. Okay, so then we would say negative 3, 1 is a solution to that system. All right, what about the second equation? Well, our first equation is 5y equal to 2x minus x. Okay, and our second equation is y equal to 3x. All right, well, we simply plug in our value of, say, negative 3. Does that equal 2 minus a negative 3? And I messed up here because y is not negative 3. Y is positive 1. Okay, so does 5 times 1 equal 2 minus negative 3? Well, 5 times 1 is 5. Does that equal 2 plus 3? And that indeed does equal 5 equals 5. All right, what about the second equation? So does y equal to 3x work as well? Does the ordered pair work for that as well? Well, y is 1. Does that equal 3 times a negative 3? And clearly 1 is not equal to negative 9. That is not a solution. In other words, it checks for the first equation, fails the second equation. Therefore, negative 3, 1 is not a solution. Okay, so systems of equations in two equations and two variables can be solved by graphing. So a system of linear equations can be solved by graphing. Since each equation in the system represents a line, the solution to such a system is where the graphs intersect. Okay, so the graphing method, if you want. You can follow these steps if you want. Step 1, carefully graph each equation on the same rectangular coordinate system. 2, if the lines intersect, determine the coordinates of the point of intersection of the graphs. That ordered pair is the solution of the system. If the graphs have no point in common, the system has no solution. And step 4 here, check the proposed solution in each equation of the original system. Okay, so let's solve the following system of equation graphically. Okay, so for the first equation here, x plus y equals 1, we'll go ahead and just graph by finding its x and y intercepts. So its x-intercept, we know the y-coordinate would be 0, so if you cover up the y here, we could see that x equals 1. Likewise, the y-intercept, we would have 0 for the x-coordinate, and then cover up the x, we see y also equals 1. We have 3x plus y equals 7. To find the x-intercept, cover up the, well, we know that the x-intercept we'll have a y coordinate 0, so what's its x value? Cover up the y, we get 3x plus 7, which is 7/3. And so in that case, it's probably best to not solve the graph this way. It's probably a little bit easier if we subtract 3x on both sides and rewrite it in slope-intercept form of a line. So we can see here then our slope is -3 and our y-intercept is going to be 0, 7. Okay, so let me go ahead and plot this first line in red. Okay, so we have a point at 1, 0 and 0, 1. And so if we connect the dots for these lines here, we would have a line similar to that there. Okay, and then let's go ahead and plot, say, the order pair, or it's the line 3x plus y in blue here. What? Put 3x plus y equal to 7 in blue. So we have a point order pair at 0, 7, and we have a slope of -3. So down 3, 1, 2, 3 over 1, down 3 over 1, down 1, 2, 3 over 1, and so forth. And if we graph the line, it's look something like that there. And there. And that appears to be our solution there, which is 3, comma, -2. It's a good idea to check, especially when graphing, to check whether the solution is whether the order pair is a solution. And quickly here, we're just going to do that. So for the first equation, x plus y equals 1. I'm going to check just in case. So we have 3 plus a -2. Does that equal 1? And so that does equal 1. So that checks. How about the second equation? 3x plus y equals 7. Plugging in our values, we have 3 times 3 plus the -2. Does that equal 7? And it appears that it does. Okay, in other words, that's 9. Basically 9 minus 2, which is 7. So 7 does equal 7. That checks. Okay, so the order pair 3, -2 is the solution. And once again, visually, it's sometimes can be a little misleading, and it's a good idea to maybe check your solution. So the graphs of a system of equations will usually intersect at a point, but it's possible that graphs will not have a point in common, or will have infinitely many points in common. So basically, it comes down to these 3 scenarios. If the lines are different and intersect, the equations are what we like to say independent, and the system is consistent, meaning one solution exists, and it is at the point of intersection. And so the previous example is exactly this situation. However, you could have 2 lines that are running parallel. So if the lines are different in parallel, we say the equations are independent and the system is inconsistent, and no solution exists because they don't meet, they don't cross. And if the lines are identical, the equations are said to be dependent and the system is consistent, and we have infinitely many solutions exist. Any point on the line is a solution. And so those are the 3 scenarios that you typically get when you solve a system of equations. All right, so let's go ahead and look at an example. Another example. We're asked to solve the following system of equations graphically, and see what we have here. All right, so for the first line here, 2x plus 3y equals 6. Let's go ahead and find the x-intercept. I'm going to set y equal to 0. Set y equal to 0, right? That means this guy is gone. So we have 2x equals 6. Divide both sides by 2. Gives us x equal to 3. So we have 3 comma 0. What about the y-intercept? The y-intercept, you do the same thing, except this time you set x equal to 0. And if x is 0, this is gone, and we have 3y equal to 6. So divide both sides by 3. We get y equals 2. 4x plus 6y equals 24 is the next equation. So it's in standard form, so I like to use the x-intercept method, x and y-intercept method, finding 2 points to draw the line. So the x-intercept, we set y equal to 0. That means this term's gone, it's 0. So we have 4x equals 24. So divide both sides by 4, gives us 6, comma 0. Alright, the y-intercept, once again, you set x equal to 0. So x is 0 this time. So we have 6y equal to 24 because the 4x term goes away. So we see y has to be 4. Alright, I'm going to go ahead and graph this line in red. So we have a point at 3, 0. We also have a point at 0, 2. And I'm going to go ahead and graph this. Oops. Something like that there. Okay, and that's how the graph will look like there. Alright, and then let's go ahead and graph the other line in blue. So we have a point at 6, 0. And a point at 0, 4. And this one here looks something like that. The two lines run parallel. And so we could see that this particular set of lines here or equations don't meet because they run parallel. And you probably could verify that by computing their slope to see that they're both the same. But in this case, we would say there's no solution. And the system is inconsistent. And equations are dependent or independent. Okay. The next equation here, we're actually solve the following system equations graphically. We have y equal to 1/2 x plus 2. The next equation is 2x plus 8 equal to 4y. And so for the first equation, we're given basically its slope. So we see that the slope is 1/2 and the y-intercept is 0, 2. The second equation, 2x plus 8 equals 4y. I'm going to go ahead and put it in standard form. So 2x minus 4y equals -8, just rearranging terms. I'm going to find its x-intercept by setting y equal to 0. Setting y equal to 0 will give us 2x equals -8. So dividing by 2 on both sides gives us an x-intercept of -4, 0. The y-intercept can be found by setting x equal to 0. And then solving the remaining equation. So this time the 2x term goes away. We have -4y equal to -8. Divide both sides by -4. We get y equals 2. Okay, so let's go ahead and plot this. So we have a order pair. I'm going to do this in red here. Oops. In red, the first line. So we have, okay, so let's graph this one in red here. So we have the order pair at 0, 2, and we have a slope of 1/2. So up 1 over 2, down 1 over 2, up 1 over 2, down 1 over 2. And I made a mistake there. So it's down 1 over 2, down 1 over 2. So it looks like this one. This way is looking like that. That's a little bit better. All right, and then the next question I'll do in blue, but it happens to coincide exactly with the line we already have. In other words, they're the same line. They run parallel, or they're parallel, but they coincide. In other words, they have the same line, and so in this case, there's infinite many solutions. Many solutions. The system is consistent. Sometimes we like to express the ordered pairs that satisfy the solution as, for instance, we know it consists of ordered pairs x and y, but notice y you could solve one of the equations for y in terms of x, and so basically the system consists of all ordered pairs x, y, where y is actually 1/2 x plus 2, and so for any value of x, these ordered pairs will be the solution. Alright, sometimes solving systems equations by graphing is not ideal because it's not reliable, especially if the lines don't intersect at a point with integer values. Thus, you can use algebraic techniques such as substitution. And so here's what we call the substitution method. You can follow these steps if you want. Step 1, solve one of the equations for either x or y, preferably a variable with a coefficient of 1 or -1. If this is already done, go to step 2. We call this equation the substitution equation. Substitute the expression for x or for y obtained in step 1 into the other equation and then solve that equation. 3. Substitute the value of the variable found in step 2 into the substitution equation and then find the value of the remaining variable. And then, of course, it's always a good idea to check your answers. Let's go ahead and see how this is done. So over here we're actually solving the system of equations. 4x plus y equals 13. Negative 2x plus 3y equals negative 17. Okay, so what I'm going to do here is solve equation 1 for y. And then we see that we get y equals 13 minus 4x. Okay, and then we're going to sub this into equation 2. And we get negative 2x plus 3 times 13 minus 4x equals negative 17. Alright, so we have negative 2x plus 39 minus 12x equal to negative 17. Combine our like terms on the left here, so we get negative 14x plus 39 equal to negative 17. I'm going to go ahead and subtract 39 on both sides, so we get negative 14x equals negative 17 minus 39, which gives us negative 56, and then divide both sides by negative 14, and we see that we get x equals 4. Now that we found x equals 4, we could go back into the substitute equation, right? In other words, if you wanted another name, we could have called it equation 3. So sub into equation 3. And so doing so would give us y equals 13 minus 4 times 4. So we get y equals 13 minus 16, which tells us y equals negative 3. Alright, so and then if you want to check your answer, I'm not going to do that here, but the solution is 4, negative 3. Alright, let's try another one here. Here we have a system equation where we have fractions and decimals. It's probably helpful to, say, take the first equation and get rid of those fractions by multiplying by the LCD. In this case, we have 9 and 3, so the LCD has to be 9. So we'll multiply both sides by 9. And then, of course, that would give us a new equation, 2x minus 2y equals, 1 through cancel there with 3, so equals 6. Alright, and then the next equation here, I would multiply both sides by 10, which would tell us that we would get a new equation of basically x plus y equals 2. Alright, so now we have a new equation here, equation 1 and equation 2. Alright, so I'm going to go ahead and solve equation 2 for x this time. Okay, so that would give me a new equation, the substitute equation. I'm going to call that equation 3, and x would equal 2 minus y. Alright, I'm going to sub that now back into equation 1. Okay, so let's go over here. So we have 2 times 2 minus y minus 2y equals 6. Alright, simplifying, we get 4 minus 2y minus 2y equals 6. So we have 4 minus 4y equals 6. And so subtract 4 both sides to get negative 4y equals 2. So y equals 2 over negative 4, or simply negative 1/2. Alright, so we see we get y equal to negative 1/2. Now sub this back into equation 3. So we get x equals 2 minus negative 1/2. Alright, so that's really a 2 plus 1/2. So that's going to give us 5/2. So we see the solution is 5/2 negative 1/2. Alright, another technique is something called the elimination method, or sometimes referred to as the addition method. And this method uses the addition property of equality, which states that if A equals B and C equals D, then it follows A plus C equals B plus D. In other words, when equal quantities are added to both sides of an equation, the results are equal. Alright, to perform or do this method here, you can follow these 6 steps here. Write both equations of the system in standard form, which is ax plus by equals c. 2, if necessary, multiply one or both of the equations by a non-zero number chosen to make the coefficients of x or the coefficients of y opposites. 3, add the equations to eliminate the terms involving x or y. 4, solve the equation resulting from step 3. 5, find the value of the remaining variable by substituting the solution found in step 4 into any equation containing both variables, or repeat steps 2 through 4 to eliminate the other variable. Alright, and then check your answer to step 6. Alright, let's see an example of this. Okay, so this next equation here, we're going to solve the system of equations by elimination. Alright, so let me go ahead and call this equation 1 equation 2. And what I'm going to do is eliminate the variable y. I notice they already have opposite coefficients that are opposites. And so what we're going to do is add equation 1 and 2. So we have 5x plus 3y equals 2. 2x minus 3y equals negative 16. So we're going to add those. We can see that we get 7x equals negative 14. And then now we can solve for x by dividing both sides by 7 to get x equals negative 2. Alright, now substitute back. We're going to sub into equation 1 and solve for y. Alright, so doing so, we have 5 times negative 2 plus 3y equals 2. So we have negative 10 plus 3y equals 2. So adding 10 on both sides, we get 3y equals 12, which means if we divide both sides by 3, we get y equal to 4, and that's the solution. And of course, you can check your solution. I'm not going to do that here. Is negative 2 comma 4. Let's try another example. So solve the system equations by elimination. We have 9x plus 5y equals 16. I'll call that equation 1. Then we have 3x minus 4y equal to negative 6. I'm going to call that equation 2. All right, so here we don't have quite opposites, but I'm going to go, I know that 3 goes into 9, and so I'm going to take advantage of that. And so we're going to multiply equation 2 by negative 3. And then what we're going to do is add the result to equation 1. Okay. All right, so let's multiply equation 2 by negative 3. So doing so, we get negative 9x plus 12y equals 18. All right, so now we're going to add this result to equation 1, which is 9x plus 5y equals 16. So adding these together, we see the x's cancel like we set out to do. So now we get 17y equals 34. Dividing both sides by 17 gives us y equal to 2. All right, now we're going to sub back into equation, say 1, and solve for x. All right, so we have 9x plus 5y, but y is 2, so we're going to substitute, equals 16. So now we have 9x plus 10 equals 16. Subtract 10 on both sides to get 9x equals 6. Divide both sides by 9, we get 6 over 9. Or reducing that fraction, we see we get 2/3. Okay, so that means the order pair through 2/3, 2 is a solution. All right, solve each system of equations using elimination. Okay, so I'm going to go ahead and try to eliminate, let's say, x, for instance. So I'm going to go ahead and multiply equation 1 by positive 3. And then I'm going to add the result to equation 2. All right, so let's multiply equation 1 by 3. So if we do that, we get 3x minus 9y. And it looks like I have a typo. I just realized here. My notes didn't update here. This here should be a minus 2y. My apologies. And so doing that would give us a minus 6y equals 3. Okay, so multiplied equation 1 by 3, and that's what we get there. And so let's add this result to equation 2. So we have negative 3x plus 6y equals 5. And so we can see the left-hand side gives us 0, but the right-hand side gives us 8. And that's what we call contradiction there. In other words, what this means is that there's no solution and the equations are independent. By the way, the previous one would have been there's one solution and the equations are independent as well. Alright, so that one there's interesting. Next one here, we have 2x plus 3y equals 6, 4x plus 6y equals 12. Okay, so for this one here, I'm going to call this equation 1 and 2 here respectively. We're going to multiply equation 1 by a negative 2. So I could try to eliminate x. And I'm going to add the result to equation 2. Alright. So multiply equation 1 by negative 2 would give us negative 4x minus 6y equals negative 12. Okay, so we're going to take this result and add it to equation 2. So that's equation 2 is 4x plus 6y equals to 12. This time you notice when you add, x's and y's also drop out, gives 0 on the left, but this time we get 0 on the right. And that there's an identity, as we know from previous studies. And so what does that mean in this case? That means there's infinitely many solutions. And the system is consistent and equations are dependent. But forget about to state that in the previous one, the system would have been inconsistent as well. Because it has no solution. Okay, but in any case, there's infinitely many solutions in this example. And once again, you could solve for y, for instance, 3x plus 3y equal to 6. We could write this as 3y equals 6 minus 2x and then divide by 3. Of course, this would say that we have 2 minus 2/3 x. So our solutions are of the form x 2 minus 2/3 x. So for any value of x, these quantitative order pairs would satisfy this system. Alright, let's take a look at some application problems. I'm not going to solve them, but just set them up and then let you know what the answers are. Okay, so Carrie's motorboat takes 3 hours to make a downstream trip with a 3-mile-per-hour current. The return trip against the same current takes 5 hours. Find the speed of the boat in still water. So this is what we call a distance problem. And so we'll let R here be the rate or the speed of the boat in still water, meaning no current. And then we'll let D be the distance traveled. Okay, so we know that the formula rate times time is equal to distance, or distance equals rate times time. Okay, so if we're going downstream, then the rate would be R, the rate of the boat, right? But the current is helping, so that means we get an extra 3 miles an hour. For how long are we going? Well, it says it took 3 hours, and so 3 times that rate would give us the distance. Now, if we're going up the same path, but this time upstream, with the same current, this time our rate's slower, right? Our speed is actually going down now, but we're still traveling a certain amount of time, and this time with the current going against us, the rate is r minus 3, and took 5 hours to get back the same distance. Okay, so our system of equations here is D equals 3r plus 9, or D equals 5r minus 15. Of course, you could use substitution or elimination here to solve this, but basically you'll see that the rate, or R, would equal 12. And so the speed of the boat in still water is 12 miles per hour. Yeah, so that's a typical rate times time equals distance type of system. And another common type of application for these types of problems is called a mixture problem. So a snack company sells caramel corn worth $2.50 per pound and honey roasted mixed nuts worth $7.50 per pound. In order to get a 20 pound of a mixture worth $4.50 per pound, how much of each snack should be sold? Okay, well, if we let X, say, equal the amount of, say, caramel corn, and Y equal the amount of the honey roasted mixed nuts, well, and you're trying to make a 20-pound mixture, well, one equation that you're going to get for sure is that the sum of X plus Y is 20. Right, so the number of pounds has to equal 20 pounds, right? The sum of X plus Y, the sum of X and Y has to add up to 20 pounds, right? Okay, and the other one is where the mixture comes to play. So, you have 20 pounds, and this is going to sell for $4.50. And so what you get there is $90. And so, well, to get, so not $90, but 90, the value of the mixture would be $90. So now, how much of X are you contributing? How much is that contributing to that $90? Well, the caramel corn is selling for $2.50. So $2.50 times X would be that, how much the caramel corn is contributing. And, well, the roasted mixed nuts selling for $7.50. Why? So that's how much of the nuts is contributing to that $90. Okay, so that's your system there. And to solve that, you could use elimination and substitution, but you would get Y equals 8 and X equals 12, meaning you would have to use 12 pounds of caramel corn to add to the mixture, and 8 pounds of the honey roasted mixed nuts, so that you could sell the mixture for $4.50 per pound, and in this case 20 pounds worth. Alright, that's it for this video.